So we will. So I forgot to change the header again. I'll fix that. Okay, so introductory fracture mechanics. So how many people took Professor Ghazi Saeedi's class? Okay, so we're going to actually be looking at some things that she didn't cover there. Like I want to take a look at where the stress intensity factors come from, how those are derived, and that involves actually some theory of elasticity. So we're going to take a look at, introduce you to some ideas like the very classical ideas like the Airy stress function that people might not have seen before, but I think it's good just to look at it once, so at least when the term comes up, you understand what is meant by a stress function. Has anyone taken a formal theory of elasticity course in your undergrad? And strength of material, if you were mechanical, or anyone mechanical or civil as undergrad? Did you, in strength of materials, did you look at different stress functions? The Maxwell stress function or the Airy stress function? Just a little bit, yeah. Okay, so the general idea, most of fracture mechanics is very much a continuum concept, right? So when people talk about defects, they don't mean crystal defects. Right? We're not talking dislocations, grain boundaries, or point defects, right? They mean cracks, inclusions, big particles, things that act as stress concentrations, right? A nick in a surface is a material defect in the fracture, right? So we're talking about things that are typically, say, an order of magnitude larger than what we would normally consider a defect. However, that's not necessarily true, right? We talked about how the intersection of twin boundaries gives a stress concentration, and that's a spot where cracks can nucleate from, because you don't have complete degrees of freedom with respect to deformation there. So we'll start from the premise that all materials contain a myriad of defects at multiple length scales. All right, and understanding how these defects affect the ultimate strength of the, I don't want to say, material is probably a poor choice of word, right? Affect the ultimate strength of your component is fracture mechanics, right? And really, the idea here is defect tolerant design, right? We can't ever get rid of defects where cracks can nucleate, but how can we design it so that our cracks are less likely to grow and spread, right? And what we're going to talk about today is really relevant for fatigue, right? The initiation and growth of cracks. And I'll do just a little bit on fatigue coming up. But, you know, here's a fracture surface, right? And we'll look at some fractography later, right? But basically the origin is here, right? And we'll talk about how to interpret this, but this is a extremely brittle fracture. Okay, so this all goes back to 1921 Griffith fracture theory. You probably have seen at least this idea before, right? And what Griffith did was a fairly straightforward analysis and said that if I have a crack, if this crack is going to grow, the potential energy reduction of the system by the relaxation caused by this crack growing has to be equal to or greater than the energy cost of creating a new surface, right? If this sample breaks completely, what happens to my stress? Goes to zero. My strain energy, stored strain energy, is all released, right? The penalty for that is I need to make an interface here, right? So our source of potential energy is our motion of outer boundaries, right? And our stored strain energy in the system, right? And this analysis is always assuming that the in-plane dimensions are large compared to this crack, right? So the standard geometry is we have an elliptical crack of length 2a, right? And we want to extend it some delta A, right? And this plate has a thickness b here. And that essentially it's infinite in the x and y directions in the plane. Okay. So right from Griffith then took some work from 1913 from Inglis and the theory of elasticity, right, and calculated sort of what the change in potential energy as a function of the geometry, right? The surface energy of the crack, right? This gamma S, right, is our specific surface energy, right? So we have the change in potential energy, the potential energy, the surface energy, that gives us the total energy of the system, right? The critical condition, right? We find the critical points of our system, right? Take the derivative of the energy with respect to our crack area with our change in crack area. Oh, I forgot to point out, right? This term here, this is an effective modulus value, right? And depending on, where did it go? Plane stress or plane strain, right? It is either going to have this Poisson's ratio term in it or not, right? So for plane strain, it has this. Plane stress, we have this. Right? So if our crack area is 2b, right, this is our crack area, this is our critical condition, we solve for stress, and this is essentially the stress required to initiate fracture. Right? So it depends on the modulus, the stored energy, the specific surface, and the geometry, the size of our crack. Right? So what is B? B is the thickness of the plate. Right? The important thing to know here is the second derivative is negative. Right? So if the second derivative is negative, once this crack starts, it's just gonna, right? It's an unstable configuration. So once you're at a stress where this crack starts to grow, from the Griffith analysis, the crack propagation just completely goes off, right? So physically, that means this is only going to work for brittle materials, right? If you have ductile materials like a metal, we need to make adjustments to the basic Griffith analysis, right? And that was done by Orawan, right? Orawan these metallurgists in the 30s, 40s that were working with dislocation theory, and like these guys, their names are everywhere, right? They just kept they just kept pumping things out. There's no way that I'm ever going to have my name on as many things as Orwan or Cottrell, right? But anyway, what Orwan did is basically make a adjustment, right? We have the surface area, but he also put a plastic dissipation term in here, right? So this gamma P is the amount of plastic work done per unit area of the cracked surface created, right? And the assumption is that this is going to be significantly higher than the surface energy of the fracture surface, right? So this inclusion of this plastic term has a yeah.
Previous.
What's that?
Previous.
Oh, no. This.
What was the difference between ductile and brittle material?
What's that?
What was the difference between ductile and brittle material?
Okay. In crack growth, so in the brittle material, there's no plasticity, right? So it just depends on, you're balancing the potential energy of your system against the surface of the crack, right? For brittle material, you allow dissipation of energy through plasticity, right? So not all of the stress you put into the material is going into stored strain energy. Some of the, right, you're dissipating energy through plasticity, and right, that essentially increases the amount of stress that you can have. Right. And so that's sort of the main idea behind Griffith, right? If we look at the energy released, here we have a crack at the surface. Right, if we want to look at the total mechanical potential energy of the cracked elastic body, we have the stored strain energy here, and we have the work done by external forces, right? And you have a contribution from both of those terms.
So what are those terms?
This is the strain energy. This is the work done by external forces.
Work done by external forces is stored as strain energy, right? Look at it. Work done by external force is stored as strain energy.
Yes. Well, you have. Let me think about this for a second. Right? You have this includes it was super obvious when I threw it in the notes because I hadn't thought about it for years. Now that I'm right, this is straight. This has to include the dissipation. It's surface energy, plastic energy, right? So this, yeah. Right? So those of you who just took fatigue and fracture. I'll have to look this up and go back through my notes. Right. I don't work in fracture, so I spent time reviewing the hard stuff, not the easy stuff. And now the easy stuff is tripping me up. Right. Let me go back and look at that and see exactly how.
The units are different.
No. The point is that if say this is a specimen, right, and I put an external load here, right, with no dissipation, the work done macroscopically should equal the work done microscopically, and then this becomes identically zero, right? And according to this, then there's no potential energy driving force for the crack, which doesn't make sense, right? So there's a definitional mismatch in my brain right now going on, right? That's what your question was getting at, right? And it seemed really obvious when I threw the equation down on paper, but now. Right. And now I've lost my groove. So how do I go from there to there? Right, okay, so this is just this here. That's the stress required. This is, right, this part of Griffith's criteria, if we just move this over to this side, when these two are equal, right, when this term is equal to the stress, that's when we're going to have. So it's not recast, it's just rearranged, right? Then what people do from an engineering point of view is this crack compliance of a solid with a crack, where we measure displacements as a function of the applied stress, applied load, right? And we can rewrite this Griffith criteria in terms of the crack compliance, right? And what this allows us to do is we can then have our crack sample, we can measure our end displacements, and at the same time measure our crack extension. And from this, we can get estimates of our energy release rate. Right? And again, this just allows the energy release rate to be evaluated.
Can you get one from that? How do you go from that equation to this equation? You don't have U in the first one, right? You have crack.
Yeah, so you need to go through theory of your elastic theory, right?
So it's not only that equation.
It's not. Well, yeah. You write stress as a function of strain displacements, right? You use isotropic elasticity, so you can write this in terms of displacements. It's not straightforward to go through. Right. There's an initial analysis, and in fact, in the reading, you need to go to a fairly advanced book on fracture to see it work out right. If you look at the chapter from Courtney and Hertzberg that I'm going to post, right? They just say it can be shown, right, and jump to this this equation, which essentially means there's 4 pages of derivation going from here to here. Okay, so we have 3 basic modes that we want to consider of how a crack can open, right? And this is just nomenclature, right? Mode 1 is tensile opening, right? The crack faces separate in a direction orthogonal to the face of the crack, right? We have a symmetry of displacements. right? The XZ, top above and below this plane, and the XY plane, side to side of this plane. We have a symmetry of displacements. Mode 2 cracks, this in-plane sliding mode, right? The crack faces are mutually sheared in a direction orthogonal to the crack front. The crack front is here, and we're shearing perpendicular to it. The displacements are symmetric with respect to the XY plane, and they're anti-symmetric with respect to the XZ plane. Meaning that if you're a certain distance above the plane, you're going in the positive direction. A certain distance below the plane, you're going in the negative x direction. All right, and these crack face displacements and motion of the crack are analogous to how an edge dislocation works. Right. Mode 3 crack is this anti-plane shearing. Right? Crack faces are sheared in the direction parallel to the crack front, right? And we're anti-symmetric with respect to the XY and XZ planes. Right? And the displacements and motion are analogous to a screw dislocation. Right? You basically think of doing a Burger circuit around this, and you have a step displacement of this original surface. Okay. So now we're going to jump into linear elastic fracture mechanics. And I say here, looking at the plane crack problem, so we're doing essentially a 2D analysis. It's going to be either plane stress or plane strain. And I say simple, and I mean, in the grand scheme of things, it's simple, but I don't expect anyone to get all the details and follow all the details and work through it, right? This is really, I want to show the process and introduce some ideas from classical elasticity, right? And then this is going to work through and formulate the critical condition for the growth of cracks, right? So we're going to develop the idea of stress intensity factors and show how those stress intensity factors are derived rather than just sort of spitting them out, right? So we start with some absurd assumptions, right? We've got a semi-infinite crack and an infinite homogeneous and isotropic medium. Okay, so what do we mean by semi-infinite crack? Right, so this is our plane. This plane is infinitely large, and this crack goes from 0 to negative infinity. Right? It's exactly halfway through our infinite crack. All right, and the rest of our not uncracked region goes from 0 to positive infinity. Right? And what we want to do is develop an expression for stresses and strains and displacements near this crack tip. Right? Okay. So for this, I took a bunch of slides from a really good set of course notes from Professor Ramamurthy, right? From IIS. Did you ever have a course with him? No? It's a very well-known mechanics guy. He's also an editor for ACTA. But you were also IIS, right? Did you didn't? No? Were you in materials or mechanical? Okay. But anyway, he did his PhD at Brown, I believe, with Alan Needleman. But anyway, a very nice guy and a really excellent mechanician. And he has a really good set of lecture notes, and rather than retyping all of this, since I'm trying it out, I don't know how well this is going to go over. It might go over like a lead balloon. If it works well, I'll condense and revise and type this up. But for now, as for a first time through, use his notes. So we have to set up the problem, and everything here is done in polar coordinates, right? So we have a cylinder, or we're in a plane, so we have a circle around our crack tip, and just in terms of notation, sigma RR is a radial direction, right, along a radius, right, specified by a theta, right? So for a given angle, let me just, right, so here's a circle, right, and we have a theta. This here is the RR direction. The tangent to this is the theta direction. And then a shear in this plane is the R theta or theta R, right? So you can imagine for any theta we pick, we can define the direction given by the radius and the tangent, right? And so that's just the nomenclature for the stresses in polar coordinates. And you had to do it as an exercise. There was a question to ponder about writing things in polar coordinates way back. But the equilibrium equations are here. Right? This is what stress equilibrium looks like in terms of polar coordinates. We've got these 1 over r terms here because we have to think about the invariant measure, the differential, right? When we do derivatives in terms of polar coordinates, the transformation that needs to happen here. We have our strain displacement relationships. So how we go from displacements, or displacement gradients to strains, right? In terms of polar coordinates. And we also have to consider strain compatibility, right? Is the strain field that we're coming up with actually allowable? Right? We're not going to do much with these equations, but this is just sort of setting up the stage for what we're going to do, right? Anytime we start with a classical elasticity problem, we start from these basic steps, right? So this has to be true. Stress equilibrium has to be true, right? Compatibility means, with the exception of the crack that we're doing the analysis around, right? We're not overlapping material points, right? We're not mapping two material points to the same point, right? We're not opening any holes, and points that are infinitely close before the deformation remain infinitely close after the deformation. Infinitesimally close, right? And so that's what the strain compatibility equations guarantee. So we have Hooke's law, right? And if we work through the Hooke's law equations for plane stress, we have this set of equations. For plane strain, we have the Poisson's term, right? For plane stress, the ZZ term is equal to 0. For plane strain, the epsilon ZZ term is equal to 0, right? So we have, in this case, we have for plane stress, we have a thinning of our plate, we have a strain in the ZZ direction, and we have essentially a 0 stress, we have a free surface condition. For plane strain, we can think about that as a very thin sheet out of an infinitely large block, right, where we have no strain in the ZZ direction, but we do have a stress because we're confined by the other material, right? And this is just Hooke's law. It just looks weird because instead of writing it out in matrix equation, we're writing out in regular form with, and it's in polar coordinates, right? Okay. So for the plane problem, right, we need to guarantee that our solution satisfies stress equilibrium. So to do that, we introduce something called an Airy stress function. And basically, the Airy stress function is a change in variables. Right? We're going to have a differential equation in terms of compatibility and equilibrium. So what we're going to do is we're going to do a change of variables that guarantees that stress equilibrium is always going to be satisfied. Right? It's just a mathematical trick. Right? We're going to rewrite our variables with this new variable, in this case speed in polar coordinates chi, right? Goes back to Airy in 1862. We write our stresses in terms of this new function, and then we have a new differential equation that can be solved more easier than the classical elasticity equations, right? So what we do is we define some function such that the second derivative of it with respect to y is our stress, our xx component. Our second derivative with respect to x is our yy component. And the mixed second derivative is our shear component, right? It's only defined for 2D, for 2D problems, right? And essentially, we can rewrite our compatibility equations here, right? And they both have this term, which is what's called the biharmonic equation, right? And basically, what the if we using this Airy stress function, right? We can rewrite the problem of determining the stresses in our elastic body to finding a solution for this partial differential equation that meets our set of boundary conditions, right? The key thing to notice about this, right, is it works out nicely because any polynomial of degree 3 or less will satisfy the biharmonic equation, right? So we find a polynomial, we plug it in, we guarantee that we're going to satisfy stress equilibrium. We take our derivatives, right? We have a stress field, and that's going to be an admissible stress field under some set of boundary conditions, right? So if we take our Airy stress function to be some constant times y squared, we plug it in, we take our derivatives, we get sigma xx is 2a, sigma yy, and sigma xy is 0. So this Airy stress function corresponds to a state of uniaxial tension, right? So we have dxy is a state of pure shear, so these are sort of trivial. But any polynomial of degree 3 or less is guaranteed to give you an admissible stress field under some set of boundary conditions, right? And so the purpose of introducing this is just sort of so you see the term, right? Because these are things that come up a lot, right? If you go through Hirth and Lotha, right, and you look at the stress field for an edge dislocation, it says if we assume an Airy stress function, we can come up with the field for around this, right? I don't expect you to work through this and be able to solve a problem using this technique, but at least you see the technique, because it does come up in discussing stress fields around defects and grain boundaries and things like that. Occasionally. So the in terms of polar coordinates, our derivatives of our Airy stress function are related to our stress components by this set of equations. Right? And so using these definitions for stress and Hooke's law, we can write express our strains in terms of our stress function. It's important to remember the stress function itself does not have a physical interpretation, right? It's just a numerical, mathematical trick, right? Okay. So our biharmonic equation looks like this. And now we need to think about what the boundary conditions need to be for our crack problem, right? In this case, we need to think about as theta equals plus and minus pi, right? Meaning that we're parallel, we're aligned along the crack, right? We need to have a traction-free crack surface, right? And so we need the theta term, right? So if we have a crack here at this tangent, if this is a crack, this theta term needs to be.
So where is the origin of the crack? Center or the edge? Origin of the system. Because the center of the crack or the edge.
It's an infinite plane, so the origin is 0. So the tip of the crack is 0, and it starts at negative infinity, and the crack tip is at 0. Right? So if we have this crack here, this needs to be stress-free, right? This is a free surface, and obviously shears along this plane need to be 0. For plus and minus pi, the only condition on RR is that the stress field should go to 0 as we get infinitely. No, that's not true in this case, right? Because we're still applying a macroscopic load. There's other geometries where you have the state that your stress has to go to 0 far away. Not for this one. Okay. So we need to find a stress function that satisfies as a solution to the biharmonic equation, right? And we also know that it has to have a singularity right at the crack tip, right? We have an undefined condition at r equals 0, right? So again, in the tradition of solving differential equations, we pick a form and guess and check, right? Essentially. And we're just about out of time. So before bouncing into the nasty derivation, we're going to stop there and we will wrap it up. Because there's no good stopping point. Taking it there. But really the idea here is what we're going to do is we pick a form for the area stress function, right? Plug it, figure out what we need to do to that form to make it solve the biharmonic equation, right? We then have a solution with a symmetric part and an anti-symmetric part, which corresponds to different crack modes. We can work through the solution, get the stress state, and that allows us to determine what the stress needs to be for that crack to grow, right? What the stress tip is, right? But that's where we're going with this, and we'll pick it back up on Monday. Okay. Okay. So where we left off, we were working through where this idea of a stress intensity factor comes from, right? This is the K1C values or something that you probably saw even in your introductory material science course. but where does it actually come from? And I decided to take an opportunity to detour into some classic theory of elasticity, because to derive those, we need to introduce something called the Airy stress function. And basically, the idea behind this is just a change of variables that allows us to solve the equilibrium, stress equilibrium, and strain compatibility on arbitrary boundary conditions a little easier. And we introduce some function that the derivatives of it give us the second derivatives of it give us the stress terms of interest. And if we plug that into the compatibility equations, we get terms that involve this biharmonic equation. And the way we set this up is any valid solution of this is also guaranteed to satisfy stress equilibrium. Right? So that's the benefit of it. We're guaranteed to get a solution that satisfies both compatibility and equilibrium. Right? So, of course, this is a partial differential equation, so this is not sufficient to find a solution to this. We also need to specify the boundary conditions. Right? So, depending on what boundary conditions we put in, we can do some really elementary examples. And if we make our Airy stress function quadratic with no constant term in y, that turns out to be a uniaxial tension in x, right? If we make it a mixed quadratic, we get a state of pure shear, right? And we can superposition holds, right? Any solution to the differential equation, a linear differential equation, there's a linear combination of the solutions also has to be a solution. Right. So, in terms of polar coordinates, the biharmonic equation looks like this, and we need to specify boundary conditions. These boundary conditions basically just say that the crack surface has to be tension-free or attraction-free, right? Because those are free surfaces. Free surfaces in our body. And we also know that there's a singularity at the crack tip. So generally just the time-honored method of solving PDEs analytically is guess and check, right? Come up with solutions of certain forms. The fact that it's a linear equation helps us a lot. That means we can put it into some standard lookup. And basically we get solutions that look like this, right? We have a symmetric part, end up having a symmetric part and an anti-symmetric part. Right? The cosine term and the sine term, and the symmetric part provides the mode 1 solution, and the anti-symmetric part, mode 2 solution. Remember, mode 1 is opening like a duck, right? Mode 2 is shear back and forth this way, right? And then how do we go from this to the actual solution is we apply the boundary conditions, right? And then this gets a little esoteric because we have this lambda parameter here, right, which has this lambda parameter pointing at my screen like you can see it. right? After we apply the boundary conditions, we have these, right? And because this is periodic, we have basically any set of integer solutions that will work, right? And again, I'm not expecting anyone, for those who are interested, can work through the derivation themselves. There's enough information here. The idea that I wanted to get out was just sort of what the general approach is. So there's a huge number, there's an infinite number of possibilities for this lambda parameter. So we need to constrain it, and the idea is then we bring back in a physical argument that says something about the strain energy from the crack tip, right? And so the strain energy is given like this, and it's going to be proportional to this, the radius to the 2 lambda parameter, right? And right, basically the idea is that we don't want the strain energy to go to infinity at the singularity. So we put in a very simple simple bounds, right? And as we integrate from some R naught to some R1 value, basically integrating, if this is the crack tip, right, over some angular region around the crack, R0 and R1, as R0 shrinks smaller and smaller, this strain energy should stay less than infinite. And that gives us still a set of physically meaningful values. Right? So we take essentially the most dominant term, plug it in. This gives us the area stress function. Take the derivatives, and we have a stress that looks like this, and then a bunch of higher order terms that gets neglected. Right? So that's the calculus of it. Right? And this is now our stress intensity factor. Right? So we can basically, this is what you see in all the textbooks. Okay, so that's where it comes from. Now we need to think about how to right, this just basically plugs into Hooke's law, right? How we get strains. Right. And so we can basically go through the same process for the other modes, right? And people have done this for a whole bunch of different geometries, right? So if you're actually doing this design, right, and you want to know what the let me think. The case that I had to use it for in an analysis once was it was actually a washing machine, right? So you have remember the old washing machines that had only one big knob on the front, right? And you turned it, and then you pulled on the knob to start it, right? You set it to your, right? So that's not a threaded screw, right? And so the knob that I was looking at, actually, it broke on the thread. So the top of the knob came off, right? And the part of the knob remained on the threaded screw. So what was happening was as you screwed the knob in, the thread would bottom out, and it would force an opening mode in the threaded area on the knob itself, and then you put a superposed stress on top of that, right? Gave you a bigger mode. And guess what? The actual stress intensity factors for the internal of a 60-degree V screw thread was in this book, right? Every possible geometry that you can think of, the stress intensity factors are there. And they're all worked out by basically this same procedure, right? You just start with different boundary conditions when you work out this asymptotic analysis, which is why even though we don't go through the math, right, and I guarantee probably only one or two people in this class are actually going to work through the example that's here for their own interest and enjoyment, I think it's sort of worthwhile just to see in principle how it's worked through, right? So why is this stress intensity factor useful? We talked about how to derive it, but we didn't actually say sort of what it's used for, right? And the idea of the stress intensity factor is it takes all this geometry into account. So if you have two plates, one with a crack of some length and one with a different crack, if you apply a load such that the stress intensity factors for those two cracks are the same, then the stress field and strain field at the tip of that crack are identical in both cases, right? So it's a way of doing the analysis that normalizes out all of the geometry, right? So what I can do is then take, say, for example, my weird washing machine knob case and use stress and strain fields that are calculated for a plain crack in a flat plate, right? Because I just need to figure out what the loads need to be to get my stress intensity factors to match, right? And then I can look at use my simple loading case, simple boundary condition case to look at what the stress fields are going to be for a much more complicated geometry, right? And this is really important because it allows us to scale up the results from laboratory tests to actual real-world fracture problems. And this is something I think that's sort of lost in a lot of elementary discussions of fracture, right? If you go back to, like, again, Introduction to Material Science or your undergrad mechanical behavior course, right? This is, I think, in my mind, the key idea of why a stress intensity factor is useful. And this is the principle of similitude is the key word. Right? So how do we apply this to actual analysis, right? So that when our stress intensity factor hits some critical value, that's when the crack begins to grow, right? And this is sort of the definition that everyone's talked about, right? Everyone kind of thinks of it as a Schmidt rule for fracture, right? When our resolved shear stress hits our critical resolved shear stress, we get plastic slip. When our K1 value hits our K1C value, our crack begins to grow, right? And that's sort of how this is sort of taught. But again, if we think of it within the principle of similitude, really what we tend to use this for is we know when a crack starts growing in a standard test. When are we going to get a crack that grows in our weird geometry, right? Okay. And so what are some sort of values for K critical, right? So in tough metals, hundreds, right? Polymers, brittle ceramics, and finally in non-tempered tempered glasses, right? So roughly a 2 order of magnitude change in the Kc values over sort of the family of engineering materials. Okay. So there's a lot of notes here. What I really want to sort of point out is that remember back at the beginning of the lecture yesterday, we sort of mentioned how Orawan updated the Griffith theory by including the effect of plastic energy dissipation at the crack tip, right? So if you're going to do an analysis, you need to sort of consider that, right? And get an estimate of what the plastic zone size is in front of your material and what that plastic zone is going to look like and how the plastic zone size changes as respect to the boundary conditions, right? So if you had to make a guess, would you say the plastic zone is going to be larger for plane stress or plane strain? Right? Does anyone feel comfortable enough trying to make a hard guess one way or the other? Right? Let's take a look, right? So here we assume plane stress and the material behaves as elastic perfect plastic. Right? What does that nomenclature mean? Right? Elastic perfect plastic. Right? Essentially, it means we have yielding. Right? We have at the yield strain, we have no work hardening. So we have a material that looks like this, the stress strain behavior. Right? Not realistic in the grand scheme of things, but you'd be surprised how much analysis is done in an elastic perfect plastic regime. Right? Because it's a much simpler set of equations to solve when you don't have to consider work hardening. And if you're doing design where the strains, the plastic strains are small, right? If you care about yielding, right? You don't want your bridge to yield, right? You don't want your airplane to actually yield, right? Most design is elastic. So if you're only experiencing small plastic strains, right? It's not too big of a deviation from this, and it actually going to overpredict your plastic strain, right? Which is good from a design point of view. So a lot of times we assume this elastic perfect plastic, right? And to do this, we have to assume some kind of yield criteria, right? We can use our stress intensity factors to relate. We can relate stress intensity factor to stress, right? We can then use a yield criterion, typically the von Mises, right? Where this is the yield strength, and these are our principal stresses, just like we did in the case of polymers, right? And then this just talks about, because this was from mechanical engineering, mechanical engineers don't like to do tensor analysis. They use Mohr circle to compute the stress state, which I find horribly confusing. But basically, then you get the principal stresses as a function of the stress intensity factor and the theta angle and r in terms of our polar coordinates, right? And we can find the region where we can plug that into our von Mises yield criterion, right? And we can look at the ratios, or we can look at where in our R theta space we've exceeded yield. And the important thing to know is that if we're in the plane stress case, right, we have a significantly larger plastic zone than the plane strain case. Again, not near. This is not something that was intuitive before you actually worked through it or see the figure, right? But what you have is the crack here. And you've got a plastic zone size, right? This is for mode 1 opening, right? That looks more like butterfly wings than circular out front, right? So this is where you're going to have plasticity approximated. Now this is where it gets weird, right? Because this crack here is much narrower than, say, our, right? This averages over all the grain scale homogeneity, right? This assumes a perfectly homogeneous isotropic medium, right? So when you get down into actual mesoscale mechanics, where we're worried about crystal plasticity in grain, grain shapes, things get strange, right? And so mode 1 and mode 1 for plane stress and plane strain, and mode 2, right? And notice that for mode 2, the stress, the plastic zone looks quite different than for mode 1. So if you're in a mixed mode condition, right, and our regular crack is going to be in some kind of mixed mode condition, somewhere between mode 1, 2, and 3, we have very different plastic zones, right? And then, of course, if you're doing tests, you need to make sure that your sample is significantly large relative to the plastic zone size, right? And basically, the rule of thumb from the ASME standards is you need it to be essentially 25 times the plastic zone, right? So that means ideally what we want is a test that gives us pure plane strain, because then we don't have to have a huge sample, right? So if we have a plane stress K1C measurement, right, we need a gigantic test, right? And actually you can work it out, right, that if you did that, you need a sample that would be 1.28 meters wide, right, to get a valid K1C measurement based on that criterion. If you actually were to try and build a plane stress test measurement. Okay. So that was sort of fundamental fracture theory. I'm going to jump over to looking at pictures, because I think this is a lot more fun. So fractography as a field really didn't get started much before the invention of the SEM, right? So why was optical not a good go-to tool? Right, it's depth of field, right? So for optical, the depth of field is going to be related to the alpha angle, right, of your collected light intensity, and I'll be damned if I can remember the exact equation for it off the top of my head. But basically, the wider your angle, right? So the closer your objective lens gets to your sample, the narrower your depth of field is going to be, right? If you think about a light microscope going up against the fracture surface, that angle approaches 100. Well, it's half the angle, so it approaches 90 degrees, right? Or your full angle approaches 180. So you essentially have a depth of field that's only a couple microns, right? What about TEM? TEM, right? You're far away, right? So you've got a very narrow angle, right? So that means we have a huge depth of field. But what's the problem with using the TEM? Well, it's site specific, right? But you can always sort of move your beam, right? In the same way that in optical you can change your focus plane and take a whole bunch of images, and people have done that. But more importantly, you need to have a electron transparent sample, right? So how do you make an electron transparent sample of a 3D fracture surface, right? It's something that people don't do anymore, is make replicas. Basically, you would, there is a couple different techniques, but you can make a cast of your surface, right? And then put a carbon film on the negative of your surface, and then dissolve away your casting material, right? And now you're left with a freestanding electron transparent carbon film of what your fracture surface looked like, right? You can imagine how much work that is, right? Much easier to throw it into the SEM. Right? Oh, my headline got lost. My title. This is supposed to have a heading title here: ductile fracture. Okay, so ductile fracture is characterized by these highly dimpled surfaces, right? These cavities will typically arise from inclusions or precipitates, right, where you nucleate a void that becomes further, that grows larger during yielding, right? The material between the voids necks and becomes sheared. Right? So basically, this is the micro scale equivalent of a classic cup cone failure in a tensile test, right? And to a first approximation, the depth of these dimples becomes a measure of your degree of ductility in your sample. You can see if you look at these voids here, right, we see a little particle, secondary phase particle in these. So when the inclusions become larger, or your secondary phases become larger, the ductility becomes low perpendicular to the rolling plane, right? So why is that going to happen? Right? If I've got precipitates that are preferentially, like these sulfides and oxides that are preferentially on grain boundaries, what happens when we roll the sample? What happens to our grains? They start out spherical, right? And these particles are preferentially on grain boundaries, and then we smash them flat. We do a rolling reduction of 90%. So we make our grains 9 times longer, right? Now we have essentially our particles arranged in parallel layers that are about 1 grain wide, right? And they're all aligned with their flat parts normal to the rolling plane, right? So that means perpendicular to that direction, we now have ductile material sandwiched between thin layers of brittle material. Right? And so what we see then is these large flat areas separated by a ductile failure between these particles. Right? These are called stringers in steels, in rolled steels. If you look at a cross section, actually, through the magic of the internet, I should have thought to put a figure there, but I can just pop it up. Right, Google image search. That's not what I want. Yeah, here. Right? So here's right. You get layers that look like that. That's from a high strength, low alloy. There's a more. Well, that's aluminum. But anyway, you get the idea of what the structure looks like, right? You have these, even though this is aluminum, right? If you're at the grain boundaries and you roll, you get these long parallel strips of secondary phase particles. We spend lots and lots of time talking about those in the steel section in physical metallurgy, if anyone wants to take that. Right. Okay. So another important ductile case, right? You'll notice lots of these examples revolve around steel. Why am I going to show you lots of pictures of steel? Right. What are most things built out of? That steel, right? Right. Bridges, pipelines, oil drilling platforms, things that structural things that we care about when they break enough to do a post-mortem analysis on tend to be made out of steel, right? So there's not a lot out there on fractography of ceramics, right? Why? Because they fail in a very just a straight brittle manner, right? For the most part, there's not a whole lot to be learned about the mechanism from looking at the images. Same thing with polymers, right? Fail in a very ductile manner when those crazes all link together. And you have a nice, beautiful dimpled surface. Right? So in heavily cold worked austenitic steels, they have a tendency to form shear bands and slip bands, persistent slip bands. Right? And so these slip bands here, right, become a weak point where you have very easy fracture on with a tougher ductile region here. Right? So these slip bands form an easy crack path through the structure. Right? And as you're looking at these, bear in mind that in some of these images, I know what's going on because I read the captions of the places I took them from, right? Not necessarily that I would recognize these just shown to me, right? Reading fracture surfaces is kind of an art in and of itself. So that tends to be what ductile failure. There's the archetype for ductile failure. For brittle failure in metals, we have two sort of different modes. We can either have transgranular, right, where the crack path goes through grains, right, or intergranular, where the crack path follows grain boundaries, right? So transgranular or cleavage failure tends to occur along well-defined crystallographic planes, right? In BCC metals, this is the 100 planes. FCC metals normally don't cleave under normal conditions. FCC metals tend to be more ductile, so FCC metals will either fail by ductile failure, or if you can weaken the grain boundaries, they'll fail by intergranular mechanisms, right? So stress corrosion, cracking, or internal oxidation, where you damage the cohesive strength of the grain boundaries. Okay. So for this transgranular fracture, right, the cracks are going to nucleate at sites where slip is impeded, like at a precipitate. So here we have a precipitate secondary phase particle or inclusion of some kind where we had a crack nucleate and come out. So if we look at this, remember this is an SEM image. So what's going to give us this light contrast here in an SEM?
It's an edge or a thinner region.
So it'd be an edge or a thinner region, right? Somewhere, right? Remember in secondary electron mode, our contrast is topological, right? So if you have a sharp edge, like a step, this sharp corner, right, is going to show up much brighter because of localized charging that you're going to get there, right? So these step features are actually called river markings or river patterns. You may have heard, some of you heard that term before, right? So essentially, what is this? Remember the fracture plane wants to be 100, right? But it's going across multiple grains at once, right? So essentially the system wants to minimize the surface area of the crack, right? Right. Remember the Griffith criteria, right? When the strain energy released is greater than the surface area of the crack. Right? So essentially the crack's going to follow the path of the least surface area. So it's not going to take a tortuous route and make a whole bunch of a whole bunch of turns. It can go relatively straight and follow 100 planes separated by little terraced regions that cut across from one 100 plane to another 100 plane. And depending on the orientation of the 100 planes in a grain relative to the crack, the approximately planar crack, the farther or closer these terraced steps are going to be, as the closer and farther away the river markings are going to be, right? So we can see how this looks, right? And for a tilt boundary, in this case, our fracture path is going this way, or a twist interface, our fracture path is going this way, right? And these steps are all 100 type, right? And these are other 100 linking 100 steps, right? And so these become it's just called river markings, right? This is the fracture goes across, right? We want to keep this geometry. Here, I was convinced I knew that the crack started this way and was propagating this way. And now that I look at it, I'm not so sure. Because there isn't a propagation direction given. But people who look at these all the time can tell, right, by the orientation of the river marks, right? Whether you're going, the fracture direction is going this way. So how your river marks spread, right? And so last night I thought it was going this way. Now I'm thinking it's going this way because you're spreading this way in this grain. Not sure why I thought it was going the other way last night. Right. So you got a fracture path that's moving, fracture front that's moving this way. So other cases come about. In this case, again, this is an austenitic ferritic steel, chromium nickel steels. And depending on the heat treatment, you get BCC ferrite grains with austenite at the grain boundary, right? Austenite, FCC, ferrite, BCC. So if you get a crack that forms in a grain, it will rapidly cleave across the grain, but now you've got a tough grain boundary region that has to fail ductilely, right? So the crack will propagate completely across the grain. In this case, we've got a nice flat cleavage surface with a ductile region in between, right? And then what you need to do is nucleate and get a stress that's high enough to nucleate a new crack in the neighboring grain, right? Then once that grain cleaves, then the ductile region in between will shear and fail in a ductile manner, right? So there's a lot going on in the figures, and it's made more complicated by the mechanism, right? So the mechanism to get the austenite in this steels actually is kind of confusing because you get delta iron that forms, which then decomposes at a lower temperature to austenite. Right. So to interpret these, you have to know a whole lot about the metallurgy of your system. Right? How on earth would you get austenite is typically the higher phase, the higher temperature, and when you quench, you typically get allotropomorphic ferrite. Right? You get grain boundary ferrite, not grain boundary austenite. Right? But in these systems, you can because of the decomposition from the delta iron reaction. Transgranular yeah, sorry, I thought we were changing for a second, but this is still transgranular. Right. In martensitic steels, hardened and tempered, right? So in this case, we go from FCC, we cool down. We don't have time for the carbon to diffuse away if we cool quickly, right? So we go martensitic to a BCC or BCT structure, depending on the composition. And we have 24 variants of martensite for the one variant of austenite. So this large grain essentially gets broken down into a whole bunch of small grains, each with different orientations. and they're related by packets that share the same bane correspondence, and blocks that share the same plane, and then the subblocks, right, have different orientations, right? So essentially, the difference in orientation across these different orientations hinders the directly the propagation, and we need to have shear processes, right? But notice this is in hardened. This is specifically, I say hardened and tempered steels, right? If this was just martensite, right, without any tempering, right, it would just be a pure brittle, right? Because there is no way to get any shear. By tempering, we diffuse the carbon out to boundaries, right? So we have brittle fracture across some laths and ductile across others. Right. And again, looking at these, the contrast is your friend, right? Because you see lots of steps, right? But you also see regions here. That's essentially one large clean facet. There's another connecting another large clear facet. But in between, we have shear regions. Okay. Intergranular, the crack propagates along the grain boundaries, right? So it's pretty clear the archetypical case of the crack following the grain boundaries, right? And it's always kind of cool to see grains in 3D, right? So we usually think of triple points, but remember in 3D, right, this is a triple line, right? A triple point is actually a line through 3D space, a point in a 2D cross-section, right? And your points, your grain corners, are actual true points where triple lines come together. Right, and we can see here, I don't know, the contrast isn't great, but we can see an annealing twin here. Right, so this is a sigma 3 interface going into this grain. Here, I think just 3D grain structures are just pretty dang cool. Okay. So we know we need to weaken the grain boundaries. So how do we do that? In this example, we see a crack propagating along these grain boundaries here. This was in a steel that was carburized, right? Right? Remember, everyone buys, case hardened tools, right? What is meant by case hardening, right? Is typically you give it a carburization process. So you put it in a atmosphere that is rich in available carbon, right? You can do this with a acetylene welding torch by just turning up your acetylene a little bit so your torch is making smoke, and then heat, right? And you get pipe diffusion along the grain boundaries. So you have grain boundaries that are very rich in carbon relative to the bulk, right? Quench, you get martensite, but the former austenite grain boundaries are going to be supersaturated, oversaturated in carbon. You give this a low temperature tempering, this carbon forms carbides, and now you've got a weak, like that ice cream stuff, the hardening chocolate that you put on your ice cream, right? Now you've got a rich crackly carbide shell around your grains, right? So instead of the tempered martensite structure failing like we saw in the previous one, now we have an incredibly weak grain boundary path to go along. Internal oxidation, right? Those of you in the corrosion group, right? Right. So burnt steel, right? If you anneal it below the melting point, you can get internal oxidation, right? Again, pipe diffusion along the grain boundaries, and then you get these peeling off of these grain boundary oxide shells, right? And the mechanisms of this internal oxidation is varied and confusing, right? There's a lot that can go on here, right? So you can also have intergranular failure that appears to be brittle, right? Macroscopically brittle failure, but when you put it under the SCM, it looks ductile, right? This clearly looks like what we saw with ductile failure. Here's the grain boundaries, right? These are other triple lines. These are grain boundary facets. So what the heck is going on here? Well, we get preferential precipitates at the grain boundary, right? If you have something, again, grain boundaries are great sources for diffusion. They have lots of free volume, for lack of a better word, where you can, where precipitates that have a large volumetric strain or a large coherency strain associated with them can form much more easily at the grain boundary, right? So the big ones are these sulfides in creep-resistant steel, right? So if you have sulfides dispersed through your structure, you'll often see that as you approach the grain boundary, you have a denuded zone of precipitates that contain sulfur, right? Because all that sulfur has diffused to the grain boundary where these sulfides can rapidly form. This is one of the mechanisms for these precipitate-free zones. The other is free vacancy quenching, because the grain boundaries are a good source of vacancy. So if you have nucleation reactions that depend on vacancies for nucleation points, there's not a lot of vacancies near the grain boundary because they've all been sucked into the sink. But precipitates growing at the grain boundary. So essentially we have a huge density of these ductile nucleation sites all on the grain boundary surfaces, right? And since we have a very large density, right? These are all very small. The scale bar in this is cut off, but these are micron size kind of voids that formed, right? So macroscopically, it doesn't take a lot to form one of these and link them up. So macroscopically, it behaves very brittly. Hyperlocally, it's ductile, right? But the strength of each one of these is so small that it essentially propagates through, right? So that's just some fun with fractography. Remember, Wednesday there'll be a recorded lecture on texture, right? Watch at your convenience. Monday, we will have the question and answer session about the exam. Okay, so we'll see everyone in a week. But I will be available like throughout this week, and I'll even be available on Wednesday for questions. It's just with the scheduling snafu, I have to do something at the same time as this one.